Hey everybody. Office hours today, we just have a couple things to go over so far. That is mastery questions set 15, number 1 and 2. Looking at the gas stoic report form, particularly at how we do the correction for our measured gas. And then looking at the prep activity, particularly part 2B, where you have to recognize how the information connects together. Just for everyone who's watching this after office hours, I mentioned this to everyone else already. A new video was just posted that is Dr. Neff going over the prep activity that I think will be really helpful and does a really good job kind of explaining how you can think about coupled reactions, because it is a coupled reaction problem, so it's pretty neat. But we're going to start with the mastery questions, and then we'll get to those other ideas. So mastery questions, both in set 15, question 1 and question 2, are both about these bond energy ideas. Again, Dr. Neff did a nice video on this. So let's go ahead and think about what's going on here. Whenever we think about a reaction, we can think about burning gasoline pretty easily, right? C8H18. Once it's heated up in the engine, it's in the gas state. Oh, they switched it back to liquid. Okay. I think it should be in gas state, but that's okay. There was some debate there earlier between the instructors. Plus O2 in the gas state produces CO2 in the gas state and H2O in the gas state. And really what we want to think about here is we can also have heat as a product, right? If you've burned gasoline, you know it's hot, it's fire. So we can think about, well, what in this chemical reaction is going to give us this idea of thermal energy being released. At the beginning of the quarter, we saw those ideas of light energy, or what we call photonic energy, being released as electrons changed in their energy levels. Those transitions gave rise to some release of energy. We can actually look at the same type of idea in chemical reactions, looking at the release of heat. For us, and this gets into a whole field of study called thermodynamics, which is an entire 2 quarters if you're a chem major. So we're doing just the very first kind of taste of thermodynamics. If you're taking 125, 128, you spend quite a bit of time looking at thermodynamics. So we're just getting the first kind of ideas of what is thermodynamics and how do you account for energy in your reaction, and how do you use that in your stoichiometry. And fundamentally what we're looking at so I'm going to draw the reactants. I'm going to draw the simple Lewis structures for them. And fundamentally what we want to think about is, how does rearrangement work? We're not really creating anything when we do a chemical reaction. All we're doing is we're changing where things are attached to each other. Right, and you can tell right away that this reaction, what I have is not chemically balanced, because I don't have enough oxygens to make this, and I've got way more carbons than I end up with. But fundamentally what we want to think about is, how much energy does it take to break all of the bonds around this carbon and break the bonds between this oxygen, and how much energy do I get back out when I shove that carbon together with oxygens? Right, so we're going to have to look at the thermodynamic energy associated with these things, and again, the equation sheet is going to be really important for this. At the bottom of the equation sheet, there is this list of thermodynamic values that we haven't used until now that are actually really important now. So make sure you've got your equation sheet handy. And we're going to look at this kind of similar in a way that we think about stoichiometry. We're going to think about how many bonds we break, how many we make. But before we do that, we have to think about balancing the chemical equation. Let's see, did anyone who's in office hours right now successfully balance this chemical equation and want to tell me what the balancing coefficients are so I don't do it wrong on camera for 10 minutes? Maybe I'll need 3 minutes.
I got 2 C8H8, 25 O2, 16 carbon dioxide, 18 force.
Perfect. That is correct. So we need the 2 here because we need, since we've got H2 and a single O here, notice this is O2, we need this oxygen to have, this water to have an even number in front of it. So instead of having 9, which would have given us the 18 hydrogens, we have to have 18 to get an even number. Then we need to double that. And after we get that step, 16 carbons, and then just figuring out how many oxygens we have. So when we look at this, I can think about this as I'm going to have to break up, and this is theoretical, right? When we actually do a chemical reaction, we don't break all of the bonds and reform all of the bonds. We've got transition states, all these other ideas. But in our first kind of foray into thermodynamics, we're going to say, I'm going to take 2 octanes, and I'm going to break all of the carbon and hydrogen bonds in 2 octanes. So we need to do some accounting of how many carbons that is, and how many carbon-carbon bonds that is, and how many carbon-hydrogen bonds that is. The carbon-hydrogen bonds I can get just from this. It's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18. So I'm going to have 18 carbon-hydrogen bonds, and 1, 2, 3, 4, 5, 6, 7 carbon-carbon bonds. Just to save some space, I'm going to now erase this molecule and just say that it's made out of these different bonds that we're breaking. (18) carbon-hydrogen bonds plus 7 carbon-carbon bonds. And we're going to be doing that twice because we've got that balancing coefficient up front. The oxygen's a little bit easier. We've just got the oxygen-oxygen double bond, but we're going to have 25. Let's do this. Yeah, 25, that's fine. 25 oxygen-oxygen double bond. Right, so I'm keeping my balancing coefficients out front, and then I'm accounting for the number of bonds that make up the compound inside my parentheses. Lots of different people have different ways that they like to keep track of this. I'm going to put an X there because it looks weird without it. Different people have different ways they keep track of all of this stuff, but for me, this is the way I like to keep track of it. I think Dr. Neff does it slightly different in her video, and if you were in Dr. Cantu's office hours, he does it a slightly different way as well, but this is the way that makes sense to me. So there's my 2x for that molecule, my 25x for that molecule, and this is going to be the 3 dots is the shorthand notation for therefore. So this thing on the reactant side, I'm going to be breaking bonds, therefore I need to put energy in to break those bonds apart. And then I can look down here at my product side. And I'm going to have 16. And notice for every CO2, I've got 2 carbon-oxygen bonds. So I'm going to have 2 carbon-oxygen bonds. And be careful, your carbon-oxygen, I'm showing office hours, and well, I'm showing the recording and now I'm showing office hours. Your carbon-oxygen double bond is different when it's in CO2 versus organic compounds. So there's 2 different values for carbon-oxygen bonds. And this is carbon-oxygen in CO2. So we have to make special note of that because it does have different energetic values associated with it. Plus 18x oxygen-hydrogen bonds, we've got 2 oxygen-hydrogen single bonds in every water. Making sure that there's not a difference there. Okay. Now this, and I went a little sideways, so I'm going to fix that a little bit. Now this is forming bonds. So that's going to give us energy out, that's going to be a negative value, and energy in, that's a positive value. This is different than the thermodynamic calculations you will do next quarter, where you're calculating a difference in, you're calculating a difference of a difference. Here, we are calculating just based off of bond energies and whether we are breaking bonds or forming bonds. It's not exactly the best way to do it, but again, it works really well as long as there's nothing else to consider besides the bond energy. So situations where we're dealing with gases or things that have very weak to no IMFs, this works great because that's all the energy you have to think about. If we had something with strong IMFs, this starts to become less good, and that's part of what we fix in Chem 125, 128 when we do thermodynamics. So at this point, we're just doing some math accounting. I'm going to plug in my energy for kilojoules per mole of CH, my energy for kilojoules per mole for CC, my energy for kilojoules per mole of O2, and I'm going to calculate how much energy has to be put in. And I'm going to do the same thing for these, and that will give me the heat associated with this reaction. Does that make sense? There were two people asked this, Kylie and Jacob. The one thing, I'll mention one more thing that catches a lot of people off guard here. Once you do this calculation, I don't know what the value is. I'm being a little bit lazy with it being week 9, but like, you know, it's just calculated work. The thing you have to watch out for, that's again another conceptual idea, is recognize that the energy you get here, let's just call it notice that's going to be for 2 moles the way we've calculated this is for 2 moles of C8H18. So make sure that you've got an energy of reaction for 2 moles of C8H18 because that's what you've done it for. The energy that you get out, you could actually write in terms of 4 different things. You could write it in terms of your 2 moles of C8H18, or you could write it in terms of 25 moles of O2 reacted, or you could write it in terms of the energy that's released when 16 moles of CO2 are produced, or you could do it in terms of 18 moles of H2O produced. So we actually have 4 different ways that we could write this down. So a lot of people forget that they did this calculation for 2 moles of C8H18, so they end up being off by a factor of 2. So don't forget that factor of 2. So that's question 1. You need to table the bond enthalpies. So it's asking for the energy, and then it asks for a specific number of moles. So you know you're going to do 2 moles C8H18 times 1.45 moles or whatever number you have. Question 2. Kylie, did that help you out as well?
I'm trying to figure out how you get from
Kyle, sorry.
I found the energy for the 2 moles, and I just don't understand how you get it to the
For 1.45?
moles that gives you. Yeah, minus 1.2.
Just multiply. Right? Notice your moles of C8H18 will cancel out, and you'll just get energy out. So this is the point where energy really becomes just another stoichiometric product, right? It's another product in our reaction that's going to obey these mole ratios. So I'm going to get heat per 2 moles, heat per 25 moles, heat per 16 moles. And we can actually use that just like any other product that we have. So we can use it just like that, and then we can actually, I don't know if there are any problems that do this, because I haven't looked really closely at this, but we can also do this idea backwards. And actually a lot of stoichiometry was done with the idea of heat. It's much easier to measure heat than it is to measure moles of material sometimes, whole process called bomb calorimetry. But essentially if you can figure out how much heat was produced in the reaction, you can backwards calculate and figure out how much material must have reacted. So the problems that, for problem 1 and problem 2, you're figuring out how much heat is released from the moles reacted, but you could actually do it the other way and say, well, if this amount of heat was released, this amount must have reacted. Let me take a look at question 2 and make sure that this is kind of the same way. So balance the combustion of ethanol, gives you the equation. Estimate the enthalpy change for the combustion of 1.16 moles of ethanol. So question 2 actually turns out to be the exact same process, just with a different material being reacted. So we should be able to follow the same process. Make sure, I really like when I'm doing these problems, I find it really helpful to draw the Lewis structures of the things that I'm doing. So drawing the Lewis structures and actually counting the bonds to make sure I'm getting the right number of bonds. I do that pretty much every time I'm doing one of these calculations. Jacob, if you want us to come back and look at it again in a little bit, we can, but go ahead and try to do that on your own for now, and we'll come back to it. We got a pretty short list, so we can come back to it. Okay, so going on to looking at the report form. This report form has us do things in a kind of interesting way. It essentially is asking us to imagine a perfect reaction where we get exactly what we want out of it, and then, how much would we make? And then it says, okay, well, what about if we actually calculate how much we make? What if we actually collect the gas and look at it? So the first thing is we're looking at a reaction. Look at that report form here. We're looking at the reaction of magnesium with HCl. Goes to H2 gas is the important thing, plus magnesium chloride, aqueous, that we don't really care about. And so the first thing we can do is, if we've got a mass of magnesium here, I'm just going to say 0.7 grams. I don't know what mass you have, but you got 0.7 grams of magnesium. You can convert that to moles of magnesium, and then you can get to moles of H2 gas. Right? And you don't actually have to do the experiment if you have a mass of magnesium you're reacting. So this becomes our theoretical yield. And then the question becomes, what if we actually went and got the eudometer and collected gas and took that into account? So if you watched my video on the lab, you saw you can actually collect the gas. And in order to calculate the moles of gas that you actually used, you're going to use the ideal gas law. So you're going to have PV equals nRT, where we're trying to get the number of moles that we actually collected. So we need to know the temperature, we know the ideal gas constant, we need to know the volume that we collected, and the pressure at which we collected it. And if we just do a simple kind of assumption, if we don't do any corrections for this, we might say that we've got 1 atmosphere of pressure. We've got the volume we collected. I can't remember what I collected. I think it was like 74 milliliters, something like that. And it's going to be our unknown, ideal gas constant, 0.08206. And the temperature, I think I was at 25 degrees. You'll have a different temperature in your data. but you're going to get something that's like 298 Kelvin. Always in Kelvin for ideal gas law. We plug this in, and this will be how much we theoretically make. Now, the problem is, this theoretical calculation, or sorry, this calculation from our experimental measurement of temperature and pressure has assumed that the pressure and the volume we have, so it gives us, in the actual lab palette, gives us a volume of gas collected, and it gives us the atmospheric pressure in kind of atrocious units of 30.14 inches of mercury. But it's a still very common used unit of pressure. So you're not going to have 1 atmosphere, you're going to have approximately 1 atmosphere of pressure. You're going to use your real pressure. The problem is, inside the eudometer, it's not just gas, right? So if you watch the video, we have this setup where we've got the eudometer. This is my crude eudometer picture. And inside here, we've got our gas, and then at some point, we've got some liquid that's filling in there as well. And so we have to take into account the fact that this gas has some extra pressure due to liquid water, right? If this gas was at exactly 1 atmosphere of pressure, the water levels would line up with each other, right? Because this water level essentially, it's really hard to do this without the video, so I hope you watch the video. But essentially, we could have this entire thing filled with just water, and the hydrostatic pressure, that is to say the pressure of the water pushing down, is not enough to push the water out. That's because the pressure of the atmosphere pushing down is greater and can keep the water up inside there. Once the reaction happens and we produce gas, the gas exerts more pressure and can push some of the water out, but it doesn't exert enough pressure. So our pressure is going to be made from different components. Our atmospheric pressure is going to be the pressure of the H2O liquid, right? And if we never did the reaction, if we just kind of never put the metal in, we could calculate how much liquid pressure there is if this thing was full. And that should be related to the atmospheric pressure. Might be off some, because it could be anything less than the atmospheric pressure as well. Inside that tube, after we do the reaction, we're also going to have the pressure due to the H2 gas. So there's this extra component. There's 2 things providing pressure inside there. And then we've got the problem of assuming that only hydrogen gas is inside here. Right? We have the possibility that inside our eudometer are other gases. Right? If you notice, it's in contact with magnesium hydrochloric acid, it's in contact with magnesium chloride, and it's in touch with an aqueous solution. Any one of those things could potentially put some extra molecules up here in the gas state. And then the question becomes, well, which of those are going to matter? Well, magnesium metal is not going to become a gas at room temperature, so not magnesium metal. Hydrochloric acid could actually become a hydrochloric gas, HCl gas, and there could be some amount in there, but it turns out, and we just know this because it's low concentration when it sits diluted in all this water. The contribution from the HCl gas possibility is really small. But what it's in contact with a lot is H2O gas. So we've got these 3 components that have to balance out the atmospheric pressure. The H2O liquid that's still inside the column, the H2O gas that is there accidentally, and then the thing we actually want to measure, the H2 gas. So what we have to do is we have to figure out how we can correct this. And one of the things that's most important is that we are consistent with our units. The equation that's given to you in the corrected calculations, it shows you how to calculate the pressure of the H2O liquid in torr. It shows you how to calculate the pressure of the H2O gas in torr. And it gives you the pressure in the atmosphere in inches of mercury. And we want to get our H2O gas in atmospheres, so it can match up with the units of R, 0.08206 times atmospheres, liters per mole Kelvin. Right? If we're using this 0.08206 number, we have to get our answer in atmospheres. So this equation becomes a unit conversion headache of inches of mercury torr, atmospheres torr, where we want to get everything into atmospheres. So that's the place where most people get this mixed up. Most people do okay with just plugging things in and getting numbers. I was checking what was on the other side of the board. So let's go ahead and look at that real quick. Whoa. Oh, first let me check Parity. Oh, I'm checking who asked this question. Parity and Yvette, did that kind of help solidify some of the questions you had about gas production?
Yeah, that was good.
Okay. So at that point, we have to be careful about a couple things. Pressure of liquid, H2O liquid. So we've got the difference in hydrostatic pressure. And that's where we're going to measure the height of the water in the column above the water in the beaker. So essentially, how much extra water is still in our column. These two things, the other two things in parentheses, are both for unit conversion. So we're going to have a really important thing to notice in here. This is given in millimeters of H2O, whereas our height is given in centimeters. So if you do it in centimeters of H2O versus millimeters of H2O, you'll mess up your units. So at this point, once we get this kind of like concept work of getting this idea down, now it's all just about watching your units and doing the calculation. And that's one place where people really mess up their units. The other place where people mess up their units is when you're looking at the pressure of H2O. I'm just going to call it gas. I think they call it vapor. You get this equation, 0.03861 T squared minus 21.53, 21.53 T plus 3009. This temperature needs to be in Kelvin. If you do that temperature in anything besides Kelvin, you're going to mess up the equation. And this equation is going to give you, when you finish calculating this, it's going to give you your pressure in torr. Same thing with the one up here. This will give you your pressure in torr. But a lot of people don't know that you need to do that in Kelvin. I know it doesn't say it explicitly on LabPal, but there is also the background document in the assignment on Canvas. So that's how we do the correction. And that should bring our percentage down closer to something like 100% or 98%. For this first calculation, where you're assuming all of the gas and all the pressure is due to hydrogen, you are likely to get over 100% yield. And 100% yield is something you can, or getting over 100% yield is something that absolutely happens in the real world. It just means you forgot something, and you're counting something extra as your product that's not actually your product. So if you ever get over, you know, like I never like it when people are like, give it 110%. I'm like, well, 10% of that is nonsense, right? If you ever get over 100%, something's not right. You've got some junk in there that you're counting as effort that's not effort. Sorry. Colloquial aside. But you can get over 100% yield. It just means you've got contamination or something that's providing additional pressure or something that's there that you're counting as product that's not actually product. So let's go ahead and make sure that we can do the uncorrected yield. I had a couple of people ask about this, so we're actually going to do this calculation together, and then we'll worry about the correction afterwards. So were you able to get the moles of theoretical yield just by doing the stoichiometry?
Yes, I got 0.0036.
Okay, right. So that's a fine number. We're going to write that down, 0.0036. Did you have any more digits, or did it just say use 2?
I just used those. I mean, I just kind of rounded.
I think that's fine, because now that I'm looking at the data we have, the initial mass was 0.087, so that's 2 sig figs. So 2 sig figs is the right report to use. So we'll use that. And then we have to get some other information. And I'm gonna get your information specifically so we can work on this together. We're gonna have PV equals nRT. What temperature were you given?
25 Celsius.
25 degrees Celsius. I'm gonna go ahead and convert that real quick in my head. 25 is the only one that I can convert in my head because it's so commonly used. 298.15. Ideal gas constant is also known. That's 0.08206. N is the thing we're solving for. What volume of gas did you have collected?
82.5 milliliters.
So I'm going to convert that since, again, the ideal gas constant is 0.08206 liters, atmospheres, moles, Kelvin. I'm going to go ahead and convert that, say the number again, but I'm going to convert it to liters as you say it.
82.5 milliliters.
So that's going to be 0.0825 liters. And then I just need that pressure. So, and what I'm going to need here is your atmospheric pressure.
30.14 in Hg.
So that's inches of mercury. And I'm going to go ahead and find a conversion factor real quick to get from, this is such a weird unit. I think the United States is the only place that uses inches of mercury. So I'm just going to inches of mercury to atmospheres. And what I've got is 1 inch of mercury is 0.03342, 0.03342 atmospheres. Calculator, I'm gonna switch this unit real quick because I don't like the way that looks. 0.03342. I'm gonna inverse it. So I like the way this looks better. I'm gonna do, I also had that flipped over the wrong way. I don't know if you noticed, my inches of mercury was gonna come across. So I'm gonna have 29.89. Wait, no, I'm gonna mess it up now. This is what I want to do. 1 atmosphere is 29.89 0.9 inches of mercury. Let me make sure I've got that correct. Double checking. Yep, okay. Flipping it over in my head almost went terribly wrong. So this, what I like about having it this way is we can see how many inches of mercury it takes to get to 1 atmosphere. And we can see that our pressure, whichever day this experiment was done, our pressure was slightly above 1 atmosphere of pressure, just slightly. So I'm going to do 30.14 divided by 29.89. That's going to give me, I don't even know if that's 1.0083 atmospheres. Just barely above 1 atmosphere of pressure. Approximately 1 atmosphere, right? So now all we're going to do is plug that in there and solve for N. This N should be close to 0.0036 moles, but it's not going to be exactly 0.0036 moles. Times 0.0825 divided by 298.15 divided by 0.08206. Oh, well. I'm kind of all over the place. Okay, back to organizing. Assuming I didn't make any calculator mistakes, I hope you're following along. 0.0034. Don't need that last 0 there, but that's that's what I get. Did you get the same number?
Yeah, I got the same number.
Okay. So, in this case, now hopefully LabPal will be happy with that answer, and then it's just a matter of getting your percent yield, which is going to be your actual over theoretical times 100%.
Yeah, I put it in. That's good.
Okay. Do you know where you made your mistake?
So it was just about going from inches in mercury to back conversion. Yeah.
Yeah. There's another way you could have gotten this number instead of Googling it. I just Googled it. But I think there's another. No, I think you have to Google it. It's not on here. So on your equation sheet, you've got the units that are still used for pressure in a lot of other places, which is atmospheres, torr, bar, pascals. Pressure is my least favorite unit because it's still not standardized very well. Okay, well, I'm glad that worked out. So now what we can see is we've got a percent yield that's still probably higher than we should have. And what we have to do now is we have to say, okay, so if this was my percent yield, what happens when I actually correct? Because this pressure was not just due to hydrogen gas. This pressure was also due to the liquid water pressure, what we call the hydrostatic pressure, and any other contaminant that was up in the gases with the hydrogen gas, which is probably water vapor. So we've got 2 corrections we can do that's going to bring this pressure a little bit lower when we take out those other 2 things contributing.
So then for the hydrostatic pressure in the corrected calculations, I would use the pH2O liquid.
Yes, that's for the liquid. That is the hydrostatic pressure correction.
Got it. Okay, thank you.
You bet. Okay, so moving on to the prep activity. I'm going to leave this here in case we need to work on it later. A couple of people in office hours still working on that. Prep 2B. Now this one is quite interesting And like I said, Dr. Ness' video is a good idea to watch that one first. This is actually how airbags work. Most of them still to this day. They've changed the chemical compounds they use to some degree because sodium azide is dangerous, but you have this really specific kind of thing you want an airbag to do, which is you want an airbag to very suddenly produce a huge amount of gas with enough pressure that it can overcome the force of you moving forward. And so it has a really particular thing, right? We need a reaction that's going to be, once it starts, is just like instantaneous, super fast reaction. Sodium azide has that. The problem is, in the process of using sodium azide, you produce sodium metal. And sodium metal is incredibly reactive with water and will catch on fire if it hits water. And your skin and your face and all of those things are made out of water. So if sodium metal was left sitting around, that would be really dangerous. So we have to use a second reaction to get rid of the sodium metal. And we use something else that's got a little bit of danger associated with it, potassium nitrate. Potassium nitrate is a good oxidizing agent, so it'll donate some of those oxygens over to the sodium and react it to something that's a little bit safer. And this reaction, again, is quite quick, so we're getting rid of the dangerous sodium metal very quickly. And we are left with potassium oxide, sodium oxide, and more nitrogen gas, which is nice, because that gives you more pressure. Potassium oxide and sodium oxide, still a little bit dangerous. Not nearly as dangerous as sodium azide or sodium metal, but still things that we don't want sitting around. If you get this powder, this is solid powder. If you get that powder on your skin, it will slowly cause burns. So we use another chemical to react those two things away, which is going to be the potassium oxide reacting with silicon dioxide. And silicon dioxide is a really safe material. This is, if you ever see those like little pearls that are like, in the packets, like you get beef jerky or something and they're like, don't eat this. That's got silicon dioxide in it. It does a good job absorbing moisture and kind of keeping things fresh. It will also interact with the potassium oxide to produce something that's pretty much benign and non-reactive. And that's this potassium oxide silicon compound. And the same thing happens with sodium oxide, reacting with SiO2, silicon dioxide. Again, we get a relatively safe sodium oxygen silicon compound. Now, the thing that's weird about this, so there's one question in particular that I'm getting to. I wanted to kind of talk through that logic. But the one thing we have to realize is that for this reaction, we've got a set amount of sodium azide, we've got a set amount of potassium nitrate, and we've got a set amount of silicon dioxide, even though we've got two sources of silicon dioxide, two places where silicon dioxide needs to react. So for part 2b, particularly that last calculation of how much silicon dioxide you have left over, you have to do moles of silicon dioxide minus the moles that react with K2O minus the moles of silicon dioxide reacting with Na2O to get your excess. So this is where you need to do two subtractions. And when we do these moles, we have to make sure we've got the correct balancing coefficients for these reactions. I think they're 1 to 1, 2, 3. Yeah, because it's just a synthesis reaction. This KO2 is just going to interact with that to make the SiO3 K2. Same thing with this. So they're 1 to 1 mole ratio, so that's nice. We just have to figure out how much K2O was produced here. So we can figure out our moles of K2O and how much Na2O was produced there, so we can figure out our moles there and do a subtraction. And then just make sure you're converting your moles of SiO2 to your grams to moles. Do the calculation, you get your moles excess, and it's asking for how many grams excess you have. So you need a couple molecular weight conversions in there. Does that make sense, Ashley?
Yeah, I think so. I think I didn't do the reaction with Na2O yet.
Gotcha. Yeah, and this is really similar to some of the labs we saw last week, where we were asking things like, do you have enough to do this reaction? If not, how much excess do you need? Or you've got two things that are reacting. You're reacting your acid with sodium hydroxide and with metal carbonate. Right? That was something we did last week, and it was just this idea of one thing involved in multiple reactions, and how do we deal with those multiple reaction ideas. So if you include this second subtraction, so if you don't include this one, you're going to be wrong. The most common mistake people make is they treat it like two separate reactions and they do 50 twice. They use 50 grams for this one and 50 grams for this one. They don't recognize that it's 50-gram portion for both reactions. And the thing I really like about this one, I think they took off the challenge question because it was hard. But you can actually kind of look at practical development of why does chemistry and stoichiometry matter. If you've got a bunch of excess silicon dioxide, you're wasting money, you're wasting weight, right? You're going to make the airbag heavier and more expensive without adding any extra functionality or benefits. So you can save money and save weight and actually optimize your system by looking at the stoichiometry. Typically, you want to have some correction buffer of we want to make sure we've got a little bit extra so nothing bad happens, but you can optimize your systems and make sure that you're doing things in the most efficient way possible. Chemistry.